The Giza Plateau is not a collection of monuments. It is the footprint of a single, ancient industrial project. For decades, a civilization with Bronze Age tools coordinated an operation of staggering scale. The central mystery is not simply how the stones were stacked. The real puzzle is how the entire machine functioned. How do you feed and house a workforce the size of a small city for generations? How do you source and move millions of multi-ton stone blocks? How do you maintain a continuous workflow across multiple colossal construction sites without modern plans or communications? By the end of this investigation, you will understand the invisible, masterfully engineered system that made these wonders possible. We will uncover how a society without wheels or iron organized the first and one of the greatest logistical triumphs in human history. What does it truly take for a civilization to bend its entire world toward a single vision? The scale of this operation defies easy comparison. To call it industrial is not an exaggeration, but a precise description of its ambition. We are not looking at a single monument built over centuries. The Giza Plateau represents a unified, multi-decade construction project, orchestrated with the singular focus of a modern assembly line. Within a span of roughly 60 to 80 years, under the reigns of 3 successive pharaohs, the entire landscape was transformed. The 3 great pyramids, their associated valley temples and mortuary temples, the lengthy causeways connecting them, the many smaller satellite pyramids for queens, and the vast fields of mastaba tombs for nobles, all were conceived and executed as parts of a single, grand design. And watching over it all, the great Sphinx was likely carved from a leftover bedrock knoll, becoming the eternal guardian of this necropolis. The raw numbers are staggering. Over 5 million tons of limestone were quarried, shaped, and placed. This was supplemented by thousands of tons of granite hauled from Aswan, over 500 miles to the south, and basalt from more distant sources. For the worker settlements, ramps, and infrastructure, millions of mud bricks were manufactured on site. To grasp this logistical footprint, we can draw a modern parallel. The Great Pyramid of Khufu alone contains enough stone to build a wall 10 feet high and 1 foot thick entirely around the entire country of France. The entire Giza project consumed more stone than all the cathedrals, churches, and chapels built in England throughout the entire Middle Ages. This was not a project that a civilization merely attempted. It was a project that consumed a civilization's total output for generations, redirecting its economy, its labor, and its very identity toward a single, mountainous goal. This staggering output could only be orchestrated by a command system of immense power and foresight. At the heart of the Giza machine was not just a king, but the very idea of kingship itself. The pharaoh was more than a ruler. He was the living embodiment of divine order, and his eternal resting place was a project of national, even cosmic, importance. To make it real, he wielded an authority that could redirect the entire Egyptian economy. Through his chief minister, the vizier, orders flowed down a strict administrative pyramid. Royal overseers managed entire regions, while scribes kept meticulous records of labor, materials, and food. Beneath them, expedition leaders organized the quarrying and transport missions, and on the ground, gang foremen with names like the Friends of Khufu or the Drunkards of Menkaure directed the work crews. This was not a haphazard gathering of peasants. It was a stratified, professionalized operation, one of the world's first true bureaucracies. They used early tools of management, conducting censuses to account for manpower, maintaining inventories of tools and supplies, and issuing written orders that standardized tasks across the vast site. In many ways, the Egyptian state was the first great corporation, an entity capable of planning not just for years, but for decades into the future, and the evidence of that long-term planning is etched into the plateau itself. The near-perfect cardinal alignment of the pyramids to the four directions was not accidental. It required astronomical observation and precise surveying established before the first foundation stone was set. Furthermore, the construction across Giza was not sequential but overlapping. While Khufu's pyramid was being finished, work likely began on the infrastructure for Khafre's complex. Temples, causeways, and quarries operated simultaneously in a coordinated ballet of activity. This reveals a master plan, a grand schematic that allocated space, resources, and labor across the entire zone for generations. The real wonder is not the physical strength to lift a stone, but the organizational strength to know where that stone needed to be when it would arrive and what team would be there to receive it. The true power of that bureaucracy is revealed not in the stone but in the people. For centuries, a persistent myth has clouded our understanding, suggesting these monuments were built by masses of enslaved people driven by the lash. Modern archaeology has completely rewritten that story. The builders of Giza were not a coerced underclass. They were a highly organized, skilled, and even respected national workforce. The evidence for this lies in the ruins of a city buried in the sand just south of the Sphinx, a place archaeologists call Heit el-Ghurab, or the Lost City. This was not a prison camp but a purpose-built industrial town. Excavations reveal long, barracks-like galleries that could house large teams of workers, along with smaller houses for overseers and officials. The finds here are telling. They uncovered not just tools but the remains of a rich diet, including bread, fish, and meat, medical facilities showing evidence of healed injuries, and even bakeries and breweries operating on an almost factory scale. These were not the conditions of slaves but of state employees engaged in a project of national prestige. This workforce was vast, but it was also specialized and rotating. At the peak of construction, estimates suggest between 20,000 and 30,000 individuals were present on the plateau, but they were not all there at once, and they were not all doing the same job. Think of it like a modern construction site, just on a prehistoric scale. There were skilled stonemasons who shaped the precision casing blocks, quarrymen who expertly extracted multi-ton blocks from the bedrock, and engineers who designed the ramps and levers. There were carpenters building sledges and tools, rope makers producing the miles of cordage needed for hauling, potters creating the vessels for water and food, and bakers feeding this entire city of labor. This was a complex ecosystem of interdependent trades. To mobilize such numbers without collapsing the agricultural base of Egypt, the state employed a brilliant and ancient system known as corvée labor. This was a form of national service, a duty owed to the king and the gods. For most of the year, the vast majority of the population were farmers, tending the fertile fields along the Nile. But for about 3 months each year, the annual flood covered their land, making farming impossible. This was the inundation season, a period of enforced downtime. The state's logistical genius was to harness this idle manpower. During these months, farmers would be called up in rotating crews to serve on the royal projects. They provided the brute muscle for hauling stones and moving earth, work that required numbers more than specialized skill. In return, they were housed, fed, and likely saw their service as a civic and religious duty that honored their community and secured the cosmic order. When the waters receded, they returned home to plant their crops. This system created a perpetual, renewable labor engine, one that leveraged the natural rhythm of the river itself to fuel the construction without starving the nation. The Giza pyramids, therefore, were not built on the backs of slaves, but on the coordinated, seasonal effort of a unified society, all working in rhythm with the very land that sustained them. But a workforce of this magnitude creates a secondary, even more daunting problem. How do you feed it? The logistics of provisioning 20,000 to 30,000 people, day after day, year after year, was perhaps the most monumental challenge of the entire Giza project. This was a city with no farms of its own, perched on a desert plateau. Every single bite of bread, every sip of beer, every piece of fish had to be brought in, calculated, and distributed with military precision. Let us put this into human terms. An active laborer performing heavy construction work requires a substantial diet. Modern estimates suggest each worker would need a minimum of 3,000 to 4,000 calories per day just to sustain that level of exertion. For a modest workforce of 20,000, that translates to a staggering 60 million to 80 million calories that must be delivered every single day. Primary fuel for this human engine was grain, specifically emmer wheat and barley. To produce the required bread and beer, the state needed to commandeer a significant portion of the entire nation's agricultural surplus. This was not a matter of chance but of calculated, centralized planning. Across the fertile Nile Valley, vast royal and temple estates operated as the agricultural backbone of the state. Through the tax system, a portion of every harvest was collected as grain in kind. This grain was not stored locally. It was the lifeblood of the state's projects. It was gathered, measured by scribes, and loaded onto a fleet of river barges. The Nile was not just a source of life for Egypt. It was the nation's primary highway, and it became the crucial supply line for the pyramid builders. Barges laden with thousands of sacks of grain would sail northward, riding the current toward the Giza Plateau. Their destination was not the desert construction site itself, but the valley temples built at the water's edge. These structures, often seen only as ceremonial gateways, functioned as critical logistical hubs. They were the ancient equivalent of deep water ports and distribution centers. Here, the grain was offloaded, accounted for, and then began its journey up the massive stone causeways to the plateau. At the workers' settlement, the scale of food production was industrial. Archaeologists have uncovered entire districts dedicated to baking and brewing. The bakeries were not small, domestic ovens, they were production lines. They used large, conical clay pots set in rows over fire pits to produce thousands of loaves of bread daily. Similarly, the breweries operated on a scale that could only supply an army of laborers. But the diet was not solely bread and beer, which provided essential calories and nutrients. The evidence from garbage heaps or middens tells a richer story. Huge deposits of cattle bones, many from young animals, indicate that meat, likely from state-organized herds, was a regular part of the menu, probably distributed as a reward or during festival days. Furthermore, the discovery of vast quantities of fish bones, particularly from Nile catfish, shows that fishing crews worked the river to provide a crucial protein supplement. This was a carefully engineered diet designed to maintain the strength and health of a valuable national asset. The entire operation, from the sowing of seeds in distant fields to the baking of a loaf of bread in a desert town, was a single, unbroken chain of logistics. It reveals that the true foundation of the pyramids was not stone but grain, and the administrative genius required to move it. The foundation of this entire logistical empire was stone, and its primary source lay right beneath the builder's feet. While the gleaming white casing stones and the granite for chambers came from afar, the colossal heart of every pyramid was local. The Giza Plateau itself is a massive block of nummulitic limestone, a sedimentary rock formed from the compressed shells of ancient sea creatures. For the project's engineers, this was the ultimate convenience, a literal mountain of raw material waiting to be shaped. The evidence of this great extraction is still dramatically visible today. Directly south of the Great Pyramid and wrapping around the Sphinx enclosure are vast, gaping open pit quarries. These are not small holes, but enormous scars on the landscape, some over 100 feet deep. Walking through them now, you are standing in the negative space of the pyramids. surrounded by the very walls that once held the millions of tons of stone that now soar overhead. Using this local limestone for the core blocks was a masterstroke of logistical efficiency. Archaeologists estimate that perhaps 90% of the total mass of the Giza complex, that's millions of multi-ton blocks, came from these immediate on-site quarries. This single decision eliminated the need to move the heaviest, bulkiest material over any significant distance, saving an incalculable amount of labor and time. But how do you extract a 2.5-ton block of solid limestone with only copper tools and stone hammers? The process was a brilliant application of simple physics and careful observation. Quarrymen, highly skilled in reading the rock, would first identify natural bedding planes, the horizontal layers within the limestone where the stone naturally wanted to separate. They would then use dolerite stone balls harder than the limestone to pound out a narrow trench along the desired fracture line, following the natural grain of the stone. Once a deep enough trench was created, workers would use copper chisels, a precious and relatively soft metal, to carefully carve a series of slots along the base of the block. Into these slots they would drive dry wooden wedges. The final act was one of controlled force. Water was poured over the wedges. As the wood absorbed the moisture, it expanded with tremendous pressure, cleanly cracking the block free from the bedrock along the predefined line. This method allowed for the relatively precise extraction of massive blocks without shattering them. The quarries were not chaotic pits but organized, tiered workspaces. Teams worked on different levels, extracting blocks in a sequence that likely followed the construction schedule above. As they cut deeper, they created the very ramps and pathways used to haul the stone out. The empty quarries themselves then became part of the site's infrastructure, some repurposed for worker settlements or later tombs. This intimate, local relationship between quarry and construction site meant the pyramid grew almost organically from the ground it stood upon, a testament to an engineering philosophy that sought harmony with the landscape, even while reshaping it forever. While the local limestone formed the pyramid's muscular core, its skin and soul came from far away. The final, breathtaking vision of the Giza Plateau was one of shimmering white and stark, powerful red. Achieving that vision required launching supply missions of incredible ambition, reaching hundreds of miles across Egypt to secure two specific, perfect materials. The first was the brilliant white casing stone. For this, the builders turned to the quarries of Tura and Masara on the east bank of the Nile, roughly 8 miles south of modern Cairo. This wasn't just another limestone, it was a premium product. Tura limestone is finer-grained, denser, and whiter than the local Giza stone. When freshly cut and polished, it would have gleamed under the sun, turning each pyramid into a colossal, geometric light reflecting on the horizon. But quarrying these flawless casing blocks presented a unique set of problems. Unlike the open pit quarries at Giza, the Tura quarries were often tunneled deep into the cliffs. Workers had to carve out galleries underground to follow the purest, most unblemished seams of stone. This was dangerous, meticulous work in low light and dusty confines. Extracting a massive 20-ton block without a single crack or flaw required even greater skill and patience than the work on the plateau. Once freed, each pristine block then began a much more complex journey. It had to be carefully transported overland to the Nile, loaded onto a specialized barge, sailed north with the current, offloaded again near Giza, and then hauled up to the plateau. Every step in this chain risked damaging the perfect surface that was the entire point of the effort. The choice of Tura stone was a statement of ultimate quality, accepting a massive logistical penalty just to achieve a specific visual perfection. For an even greater statement of permanence and power, the builders looked south to the very edge of their world. Over 500 miles up the Nile, near the city of Aswan, lay the source of the second critical material, red granite. This stone is a different beast entirely. Granite is an igneous rock, immensely hard and dense, forged in the Earth's heart. Working it with copper tools was nearly impossible. Yet, the Egyptians needed it for the most sacred, load-bearing elements, the burial chambers, the portcullis slabs meant to seal them forever, and the royal sarcophagi. At Aswan, the granite quarries present a landscape of ambition frozen in time. Here, you can see the evidence of techniques adapted for this brutal material. To extract a massive obelisk or a beam for a chamber roof, workers used a method of relentless pounding. Teams would swing dolerite pounding stones like large, hard cannonballs against the granite bedrock along a predetermined line. They would pulverize the stone grain by grain into a fine powder, slowly eating a deep trench around the desired block. This was a process of staggering patience and labor, a battle of attrition against the stone itself. Some researchers suggest they may have also used a technique called fire setting, where fires were built against the rock face and then doused with water, causing thermal shock and cracking. Once a monolithic block, sometimes weighing over 50 tons, was isolated in its trench, the final challenge was lifting it out. Evidence suggests they likely packed the trench beneath it with sand, then slowly dug out channels to let the sand drain away, lowering the block gradually onto a waiting sledge. The logistics of moving these granite giants down river were another order of magnitude more complex than the Tura limestone. They required the largest, strongest barges in the royal fleet, built specifically for this purpose. A single voyage from Aswan to Giza could take weeks, a slow, perilous journey where a single storm or mishap could mean the loss of a year's labor from a distant quarry. This separate, parallel supply chain, dedicated solely to premium materials, reveals the pyramid project's layered priorities. It wasn't enough to build big. They had to build with intentional, symbolic materials, accepting any logistical nightmare to embed specific meaning into the very fabric of the monuments. The hardest granite blocks from Aswan now faced their final, most brutal challenge, the last mile. We have envisioned teams of laborers, thousands strong, dragging 50-ton stones on wooden sledges across the desert plateau. The image is iconic, but the physics are punishing. The friction of stone on sand, even with water-lubricated sledges, represents a colossal energy expenditure, a constant battle against the very ground. But what if that ground was not sand, but water? A growing body of evidence suggests we have been picturing the Giza construction site all wrong. During the pyramid building era, the landscape may have looked dramatically different. The plateau did not rise from a vast, dry desert, but from the edge of a vibrant, working waterfront. This is the Waterway Hypothesis, and it fundamentally reimagines the logistics of the impossible. The theory proposes that a now-vanished arm of the Nile, or a purpose-built canal system, extended from the main river channel right to the very base of the Giza Plateau. Instead of a desert haul, builders would have used the river's own energy to complete the most difficult leg of the journey. Picture this not as a barren construction zone, but as a bustling inland port. Barges laden with Tura limestone and Aswan granite would sail north on the main Nile, then turn into a man-made or natural channel. They would navigate this waterway, perhaps with teams of men on the banks using ropes to guide them, until they reached harbors or unloading basins carved directly into the bedrock at the foot of the plateau. The heaviest stones would travel by water until the last possible moment, only requiring a short, steep haul up temporary ramps to reach the construction site. This turns a problem of overwhelming friction into one of manageable elevation. The evidence for this is not just theoretical. Geological core samples drilled around the Giza Plateau have revealed fascinating clues. Scientists have analyzed ancient pollen and sediment layers preserved deep underground. Their findings suggest that during the Old Kingdom period, when the pyramids were built, the local water table was significantly higher. They have identified layers of wetland plants and silty clay, that are consistent with a riverine or marsh-like environment, much closer to the pyramids than exists today. This research paints a picture of a Nile floodplain that extended much farther west, with seasonal channels and permanent branches licking at the limestone cliffs. Furthermore, the orientation and placement of the valley temples for Khafre and Menkaure strongly imply they were designed as waterfront structures, as literal docks for the celestial barges of the king, both in ritual and in reality. Their causeways then become functional ramps leading directly from the water's edge to the pyramid high above. If true, this hypothesis revolutionizes our understanding of the transport puzzle. Moving a 50-ton granite block on a barge, while still a monumental feat of engineering, is a different category of problem than dragging it over land. Waterborne transport leverages buoyancy, eliminating crushing friction. It allows for the movement of multiple massive blocks on a single vessel, turning a slow, grueling procession into a more efficient, scheduled delivery system. The quarries at Tura and Aswan were already connected to the Nile. A canal to Giza would have created a seamless, integrated water highway, linking extraction, transport, and construction into one fluid system. It suggests the ancient engineers were not just masters of stone, but masters of hydrology. They may have sculpted the water landscape itself, diverting and channeling the lifeblood of Egypt to serve their vision. The desert plateau we see today is a snapshot of the final stage, after the waters receded for the last time. But for those 80 years of furious creation, Giza might have hummed with the activity of a great port, where the splash of oars and the groan of ropes were as constant as the sound of chisels, all part of the relentless rhythm of building a mountain. A waterway delivered the stone, but the final ascent was a matter of raw, coordinated power. From the edge of the canal or the quarry floor, each multi-ton block now faced a journey across the plateau to the growing pyramid. The iconic image of laborers dragging stones on sledges is not just artistic license, it is a technological fact. Tomb paintings from the period, like those at Deir el-Bashar, show detailed scenes of exactly this process. They depict a colossal statue being transported on a massive wooden sledge, pulled by long lines of men using ropes, with a foreman standing on the statue's knees giving commands and another worker pouring liquid from a vessel directly in front of the sledge's runners. Crucially, these images show sledges, not rollers. The archaeological record supports this, with physical evidence of prepared roads and the remains of heavy wooden sledges found in various contexts. The choice of a sledge over rollers was a deliberate engineering decision. While rollers might seem easier, they present their own immense problems. Under the extreme weight of a 50-ton granite block, wooden rollers would have been crushed and flattened, creating constant friction and requiring an endless supply of fresh timber. A sledge, by contrast, concentrates the weight onto two sturdy runners, and its friction can be managed, even dramatically reduced, with a simple, brilliant trick. The tomb painting holds the key, that worker pouring liquid. The prevailing theory is one of lubrication. As the sledge was pulled forward, attendants would pour water, or perhaps a slurry of water and Nile mud, directly onto the ground just in front of the wooden runners. This created a slick plastic surface. The runners would glide over this wet mud, reducing the coefficient of friction from a grinding, sand-on, wood resistance to something far more manageable. Recent physics experiments have validated this idea, showing that the right amount of water can cut the required pulling force by half or more. So, what was that required force? Let us perform a rough calculation. A 50-ton granite block on a dry, sandy surface might require a pulling force equivalent to its full weight, an impossible task for any human team. But on a lubricated surface, the friction coefficient might drop to around 0.2. This means the force needed to move it is only 20% of its weight. For a 50-ton block, that is still 10 tons of pulling force. How many men does that translate to? An individual laborer working in a coordinated team on a level surface. can exert a sustained pull of around 100 pounds of force. To achieve 10 tons or 20,000 pounds, you would need a team of roughly 200 men. This aligns with the scale depicted in the ancient scenes, showing long, orderly lines of haulers. These teams did not work on raw, uneven desert. They relied on engineered infrastructure, prepared transport roads. These were not paved highways but carefully constructed tracks. They were likely made of compacted clay and rubble, smoothed and leveled to provide a firm, consistent surface. In some areas, timber may have been laid down to create a more durable roadway, especially on inclines leading to the pyramid's base. Maintaining these roads was a constant task, as the passage of heavy sledges would quickly rut and damage them. This points to the hidden, ongoing logistics behind the haul itself. The operation required a constant, renewable supply chain of consumables. Miles of heavy rope made from papyrus or palm fiber wore out and needed replacing. Wooden sledges, under immense stress, required constant repair or rebuilding by on-site carpenters, and the lubrication process demanded a steady flow of water, transported in thousands of pottery jars from the canals or harbors below. Every haul was a symphony of synchronized movement, a temporary machine made of men, ropes, and mud, all orchestrated to convert human strength into the slow, relentless progression of stone. That coordinated human machine now faced its ultimate physics problem, gravity. Hauling a stone across the flat plateau was one thing, but lifting it, story by story, to a point nearly 500 feet in the air was an engineering challenge of a different magnitude. The solution, universally agreed upon by Egyptologists, was the ramp, but the exact nature of that ramp system remains one of the most fiercely debated mysteries in archaeology. The question is not if they used ramps, but what kind, and how such a temporary structure could be built without dwarfing the pyramid project itself. Let us survey the landscape of major theories, each a different answer to the same vertical puzzle. The first and most intuitive concept is the straight linear ramp. Imagine a single, massive causeway built of mudbrick, limestone chips, and desert clay, rising directly from the quarry or canal basin straight up one face of the pyramid. It is simple in principle, easy for teams to navigate, and provides a stable, wide road for hauling, but its logistical cost is almost incomprehensible. As the pyramid grew taller, the ramp had to grow longer to maintain a manageable slope. Egyptologists calculate that to reach the top of the Great Pyramid, a straight ramp would need to be over a mile long. The volume of material needed to build that ramp could have rivaled the volume of the pyramid itself. It would have been a second, mountainous public works project built solely to construct the first, consuming unimaginable resources and covering vast stretches of the already crowded Giza Plateau. The second major theory attempts to solve this space and material problem, the spiral ramp. Instead of a single, straight approach, this idea proposes a ramp that wrapped around the exterior of the pyramid, corkscrewing upward as the structure grew. This design is far more efficient in terms of material, using the pyramid's own body as a foundation for one side of the ramp, but it introduces severe practical difficulties. Navigating the tight corners at each of the pyramid's four edges with a team of 200 men pulling a 50-ton block would have been incredibly complex, if not impossible. Furthermore, such a ramp would have completely obscured the pyramid's corners and edges during construction, making it extraordinarily difficult for surveyors to maintain the precise alignment and angles that give the structure its perfect form. How could you check the straightness of a corner you haven't seen for 20 years? A more recent and compelling theory, proposed by the French architect Jean-Pierre Houdin, suggests the answer might lie within the mountain itself. Houdin's internal ramp theory proposes that after a straight external ramp was used for the bottom third of the pyramid, the builders switched to an ingenious system inside the monument. He suggests that a narrow, corkscrewing ramp tunnel was built within the pyramid's core, following its internal structure with open notches at the corners. Teams would haul blocks up this dark, enclosed passage. At each corner, a simple wooden crane or lever system, positioned in the open notch, could be used to pivot the block 90 degrees to enter the next straight section of the internal ramp. This system solves the problems of external visibility and corner navigation. It keeps the pyramid's exterior clear for constant surveying and uses the monument's own mass to support the ramp. Evidence cited includes microgravimetric surveys that have hinted at less dense, possibly hollow, spiral patterns within the pyramid's lower sections, though this remains contested. Each theory carries profound logistical implications. A straight ramp demands a parallel industry of brick-making and earth-moving that must operate continuously. A spiral ramp requires brilliant traffic management and compromises on precision. An internal ramp shifts the challenge to complex interior engineering and a darker, more confined workspace for the hauling teams. The most likely answer, embraced by many researchers, is that the ancient engineers were not dogmatic. They were pragmatists. They likely used a hybrid system that evolved. A massive straight ramp or a series of smaller, tiered straight ramps could have been employed for the initial heavy lift stages, bringing the bulk of the core material up to a certain height. Then, as the pyramid narrowed and the blocks became smaller, they might have transitioned to a more efficient spiral system, either external or internal, to complete the summit. This adaptive approach reflects the overarching genius of the Giza project, a flexibility within a grand plan, always choosing the most effective tool for the phase of work at hand. The ramp was not a single, static object. It was a dynamic, growing and changing apparatus, a temporary mountain built to create a permanent one. The pyramid was not just a destination for stone, it was a factory floor in the sky. Visualize the plateau not as a single construction site, but as a sprawling, multi-level industrial complex, humming with simultaneous, interdependent tasks. At the base of the growing structure, the air would have been thick with the dust of creation and the sounds of coordinated industry. In designated yards, skilled masons worked at block finishing stations. Here, the rough-hewn limestone from the quarry was transformed into precise building units. Using copper chisels and dolerite hammers, they dressed each block, squaring the sides and smoothing the top and bottom surfaces to ensure a near-perfect fit. The goal was a joint so tight that a credit card could not slide between the stones, a precision that explains the pyramid's enduring stability. Nearby, in large, shallow pits, other workers prepared the binding agent that would lock everything together. This was not modern cement, but a mortar made from gypsum mined from the Fayum oasis to the west. The gypsum was heated in kilns to create plaster, then mixed with water and sand to form a workable paste. This mortar served less as a glue and more as a lubricating bed and leveling compound, allowing masons to slide the heavy blocks into their final position with slight adjustments before the paste set. The constant use of copper tools created another essential satellite industry, tool maintenance. In sharpening areas, craftsmen would laboriously re-edge dulled chisels and saws using sandstone abrasives, a never-ending cycle to keep the primary instruments of construction effective. Amidst this organized chaos, the most critical work happened at the measurement and alignment stations. Here, specialist surveyors, using simple but brilliant tools like the Merkit, a sighting instrument for tracking stars, and leveled string lines, performed constant quality control. As each new course of stone was laid, these engineers checked and rechecked the pyramid's cardinal orientation and its rising angle. They ensured that every block contributed to the perfect geometry of the whole, a process of verification that had to be flawless from the foundation to the capstone. Overseeing this entire symphony of labor was the silent, indispensable bureaucracy of the scribes. Perched on mats near the action, they tracked everything on their papyrus scrolls and limestone flakes. They recorded which gang delivered which block, noting its origin and dimensions. They logged the productivity of work teams, likely tying output to rations of food and supplies. They documented the placement of specific stones, creating a living map of the growing structure. This was not mere record-keeping. It was the central nervous system of the project, allowing planners to diagnose bottlenecks, allocate manpower, and maintain an unbroken chain of accountability from the quarry to the sky. This complex organization was not static. It was a dynamic organism that had to evolve with the monument itself. As the pyramid rose, the entire landscape of work shifted. Staging areas for stone had to move inward and upward. The ramps, whether straight or spiral, became longer and steeper, altering the rhythm and risk of the haul. Access routes for workers, water carriers, and supervisors were constantly rerouted. The once vast open work yards at ground level gradually shrank as the pyramid's footprint consumed the plateau. This required a masterful level of adaptive planning, an ability to think several stages ahead while managing the urgent demands of the present day. The construction site was a living clock, its gears made of men and stone, ticking methodically toward a point in the heavens. That relentless symphony of chisels and hammers created a voracious appetite for the tools themselves. Every strike against limestone, every careful dressing of a granite beam, wore down the soft copper edges of the civilization's most precious technology. This was not a project that could pause for a broken tool, so the supply and maintenance of these instruments became its own vital, humming industry, a Bronze Age machine shop operating at a scale to match the mountain it was building. Primary cutting tools were deceptively simple: copper chisels, saws, and tubular drills. Copper, while malleable and capable of taking a sharp edge, is relatively soft. When pounded against abrasive limestone, a chisel's edge would blunt quickly, sometimes within minutes of intense work. A single mason might go through several chisels in a single day. Multiply that by thousands of masons working across decades, and the numbers become astronomical. We are talking about the need for millions of individual copper tools over the lifespan of the Giza project. This demand created a supply chain that reached far beyond the Nile Valley. Egypt possessed some native copper, but not in the quantities required for such an industrial undertaking. Primary source was the distant Sinai Peninsula, a harsh desert region where state-sponsored mining expeditions ventured. These were major operations in their own right. Teams of miners would travel to remote wadis, establishing temporary settlements near the turquoise and copper veins. Using stone hammers and fire-setting techniques, they would extract the raw ore. This crude copper was then smelted in simple furnaces on site, often using charcoal from acacia trees to produce rough ingots. These ingots, shaped like ox hides for easy transport, were the lifeblood of the tool industry. They were loaded onto donkeys for the long, perilous journey back to the Nile, then shipped north to the royal workshops. For even harder tools like saws needed to cut granite, a more advanced alloy was required: bronze. This meant adding tin to the copper, a metal Egypt did not possess. The source of Old Kingdom tin remains one of archaeology's intriguing puzzles, with possibilities ranging from Anatolia, modern-day Turkey, to much more distant sources like Afghanistan. Acquiring it involved long-distance trade networks, likely managed through royal gift exchange or expeditions to the Levant. This means the humble copper chisel on the Giza Plateau connected the builder to a web of diplomacy and commerce that spanned continents. Once the precious metal arrived at Giza, it entered the on-site production cycle. Workshops near the worker settlements would have been dedicated to tool casting. Craftsmen, likely working with small clay furnaces and bellows, would remelt the copper or bronze ingots. They poured the molten metal into stone or clay molds to produce the basic shapes of chisels, adzes, and saw blades. These rough castings were then handed to smiths who would hammer them on stone anvils to harden the metal and refine the shape. a process called work hardening. But this was only the beginning of a tool's life. The most constant activity in these workshops was not creation, but restoration. Blunt, damaged tools flowed back from the construction sites in a continuous stream. In resharpening areas, workers used slabs of coarse sandstone as abrasive grinding stations. A craftsman would pour sand and water onto the stone and then rhythmically rub the dulled chisel or saw blade back and forth, slowly wearing away the metal to recreate a sharp edge. The sand, often quartz-rich, was harder than the copper, making it an effective, if slow, abrasive. This process was repeated countless times until the tool was worn down to a useless stub, which would then be sent back to the furnace to be recycled into a new tool. This cycle of use, where sharpening and recycling was a perfect metaphor for the entire project, an endless loop of renewal fueling perpetual progress. And the tools were not limited to metal. The stone pounders, the dolerite balls used for quarrying and rough shaping, were another consumable. Sourced from specific outcrops in the eastern desert, these hard stone spheres were essentially disposable hammers. They would fracture and shatter under repeated impact, requiring a steady supply to be brought in. Carpenters produced wooden mallets and handles, while other specialists braided miles of measuring cords from papyrus or palm fiber, cords that would stretch and wear out and need replacement. Every aspect of this tool economy reveals a profound understanding of logistics. The planners knew that the pyramid was not just built with stone, but with the durability of copper and the resilience of the systems that sustained it. The true monument, therefore, is not only in the finished form, but in the countless vanished tools that shaped it, each one a tiny, essential component in the greatest machine of the ancient world. The constant need for tools reveals a deeper truth about the Giza project. It was built by people who needed a place to live. For decades, the plateau was not just a construction zone, it was a thriving, purpose-built city. The archaeological footprint of this city, known today as Heit el-Ghurab, or the Lost City, provides our clearest window into the human engine behind the stone. Excavations here have uncovered not a haphazard camp, but a meticulously planned industrial settlement, a machine for housing labor. The layout speaks of cold, calculated efficiency. Dominating the site are 4 long, narrow galleries, each over 100 feet in length. These were not family homes, but barracks designed to house large, rotating crews of workers. Their design is strikingly uniform, with rows of raised platforms that likely served as sleeping bunks and a central aisle for movement. This was housing conceived on an almost military scale, maximizing capacity and control. A single gallery could sleep perhaps 50 men, meaning these 4 structures alone could house hundreds, with more likely still buried. Nearby, the archaeology reveals a different standard of living. Smaller, mud-brick houses with courtyards and multiple rooms were reserved for the permanent staff, the overseers, scribes, and skilled artisans whose expertise required them to live on site year-round. This architectural hierarchy made the social order visible, from the communal barracks of the seasonal labor to the private quarters of the managers. But a city of laborers cannot run on shelter alone. The most telling discoveries at Heit el-Ghurab are the facilities dedicated to sustenance. Industrial-scale bakeries have been found, with rows of large, conical clay bread molds set in beds of ash. Estimates suggest these bakeries could produce thousands of loaves per day, enough to feed an army of builders. Adjacent to them were large vats and installations for brewing beer, a nutritious staple of the ancient Egyptian diet. The scale of production here was not domestic, it was factory level, turning grain from the royal stores into the daily fuel for the workforce. At the heart of this settlement was a large, open courtyard. This space was likely the administrative and social hub of the entire operation. Here, scribes could muster work gangs, assign daily tasks, and distribute food rations. It was a place of assembly and order where the abstract plans of the central bureaucracy met the physical reality of the men who would execute them. This entire compound, with its walls, gates, and organized streets, was a fortress of productivity. It kept the vital workforce sheltered, fed, and under direct supervision, minimizing downtime and maximizing the hours spent on the plateau. Yet, this permanent town likely represents only one layer of the housing logistics. During the peak inundation season, when the corvée labor force swelled, the population on the plateau may have doubled. Where did these extra thousands sleep? It is probable that temporary camps, perhaps consisting of simple reed huts or tents, sprang up around the edges of the main settlement and near the work sites. These would have been basic, functional shelters for a rotating population that only stayed for a season. The permanent town of Heit el-Ghurab, with its granaries, bakeries, and administrative offices, would have served as the stable core, supplying these satellite camps with bread, beer, and organization. In this light, the worker settlement emerges as a monumental achievement in its own right. Before a single block for the pyramid was quarried, the state had to build an entire city to house the builders. It required its own architects, its own supply lines for mudbrick and timber, and its own permanent staff to maintain it. The lost city was the indispensable foundation, the logistical platform from which the impossible was made routine. It turns the story of the pyramids from a tale of anonymous toil into one of organized community, a society in miniature that lived, worked, and thrived in the shadow of the rising mountain. A city of 20,000 laborers cannot function on bread and shelter alone. The true test of this ancient logistics machine was not moving stone, but sustaining the people who moved it, keeping them healthy, motivated, and capable of the grueling work for season after season. The system had to account for the inevitable human costs of such an endeavor, from broken bones to broken spirits. Remarkably, the evidence suggests it did. The discovery of worker cemeteries near the lost city provides a profound and poignant window into this aspect of the operation. These were not mass graves, but individual resting places, some marked with small stone stelae, a sign of respect. Studies of the remains tell a story of hardship, but also of care. Archaeologists have found skeletons with healed fractures, including complex breaks in arms and legs. The bones show clear signs of professional medical treatment, having been set and immobilized, likely with wooden splints and linen bandages, allowing the individual to recover fully. This indicates the presence of skilled healers on site, individuals who could treat serious injuries and return valuable workers to their teams. Other remains show evidence of long-term conditions like arthritis, suggesting that even those with chronic ailments were still part of the community and received support. This level of care was a practical necessity. A trained mason or an experienced hauling team leader was a valuable asset. Losing one to a preventable infection or a poorly set bone represented a loss of skill and efficiency. The state had a direct interest in maintaining the health of its workforce, investing in their recovery to protect its own monumental investment. This investment extended beyond crisis care into daily welfare. The single most powerful tool for maintaining morale and preventing unrest was a full belly. We have already seen the industrial bakeries and breweries, but their output was more than just calories. It was a psychological contract. A reliable, plentiful supply of food and clean water was a tangible demonstration that the state was upholding its side of the bargain. For a farmer serving his seasonal duty, knowing he would receive a daily ration of bread, beer, fish, and occasionally meat made the backbreaking labor a form of secure employment, not punishment. Thirst was a constant danger in the desert sun. The logistics of water supply were therefore critical. Water was transported in thousands of pottery jars from the Nile or nearby canals, and large, lined basins or wells were likely maintained in the settlement to ensure a constant reserve. Dehydration could cripple productivity as quickly as hunger, so managing this most basic resource was a non-negotiable priority. Within this vast human machine, a sense of identity and pride was carefully cultivated. Scratched into the stones of the pyramids and tombs are the ancient equivalents of crew signatures, names given to work gangs. We find titles like the Vigorous Gang, the Enduring Gang, or the Friends of Khufu. These are not the impersonal labels of slaves, but the proud badges of skilled teams. They suggest competition, camaraderie, and a collective ownership over their portion of the work. A gang that named itself the Drunkards of Menkaure clearly had a personality and a shared spirit. This social structure was a masterstroke of human management. By organizing laborers into smaller, named units, overseers could foster team loyalty and healthy rivalry. It allowed for clear delegation of tasks and accountability. A gang would be responsible for delivering and placing a specific set of stones, their name forever linked to that achievement. This transformed anonymous labor into a legacy, giving even the haulers and masons a personal stake in the grandeur they were helping to create. The entire logistical pyramid, therefore, rested on a foundation of human understanding. It recognized that to move mountains of stone, you first had to care for the people pushing them, tending to their bodies, securing their basic needs, and nurturing their spirit of shared purpose. The steady pace of construction across decades is the ultimate testament to the success of this philosophy, proving that the greatest strength behind the pyramids was not in the ropes or the ramps, but in the sustained will of a community working together. The pyramid's rise was a clockwork of stone, each phase demanding a specific material delivered at a precise moment. This was not a warehouse project where supplies could sit idle. It was a masterclass in synchronized, phased logistics, an ancient system we might call the pharaoh's just-in-time delivery. The construction sequence itself dictated a strict calendar of needs. The initial decades focused on the core, consuming millions of tons of local limestone in a steady, predictable rhythm from the quarries just yards away. But interwoven with that foundational work were the critical, non-negotiable deadlines for premium materials. Consider the granite beams for the king's chamber in the Great Pyramid. These monolithic slabs, each weighing over 50 tons, had to be high above the desert floor, perfectly positioned to form the chamber's roof. They could not be installed early, as they would block the internal ramps and pathways needed to build upward. Nor could they arrive late, as their placement was a prerequisite for the layers of stone that would be built above them. Their delivery and readiness had to be timed to the exact month, perhaps even the exact week of the construction schedule. A delay meant the entire intricate ballet of labor on the plateau would falter, with thousands of workers left waiting for a key component stranded somewhere on the Nile. This precision extended to the dazzling Tura limestone casing stones. These fine white blocks were the final skin, applied from the top down as the pyramid neared completion. Bringing them to the site too early would risk damage during decades of other construction activity. They had to arrive in sequenced batches, their quality protected, ready to be lifted into place as each level was prepared to receive them. The entire project, therefore, operated on a dual timeline, the steady drumbeat of local core material and the perfectly orchestrated crescendos of imported granite and casing stone. This astonishing coordination was made possible by locking the entire supply chain to the heartbeat of Egypt itself, the annual Nile flood. The heavy barges carrying Aswan granite could only make their 500-mile journey effectively during the months of the inundation. When the river swelled, it created a deeper, wider channel, allowing these colossal vessels to navigate more safely. The floodwaters also reduced the distance of overland hauling at the quarry site, as the river would lap closer to the extraction areas. The state's planners knew this. They would have calculated backwards from the planned installation date of the king's chamber beams, factoring in the months-long voyage north, the offloading process, and the final haul up to the plateau. An expedition to Aswan would be commissioned years in advance, with the quarrying of the specific beams timed so they were ready to load onto barges the moment the floodwaters rose. A missed flood window meant a one-year delay for that entire component, a catastrophic setback. This forced the project into a beautiful, brutal symbiosis with nature. The inundation season, which supplied the agricultural surplus to feed the workers, also opened the aquatic highway to bring them their most critical tools of stone. The administrative genius lies in the documents we no longer have, the papyrus scrolls that must have existed, detailing multi-year material forecasts, quarry outputs, and barge schedules. Scribes were not just recording what had happened, they were scripting what must happen next, aligning the slow growth of a mountain with the eternal, predictable rhythm of the river. The colossal guardian of the plateau was not an afterthought, but a project born from the same logistical genius. While thousands hauled stones for the rising pyramids, another massive team was engaged in a different kind of creation, one of subtraction. The Great Sphinx was not built, it was revealed. The entire monument was carved directly from a single, leftover knoll of the same nummulitic limestone that formed the plateau's bedrock. This was not a separate artistic endeavor. It was a brilliant, concurrent operation that solved multiple logistical problems at once. The act of carving the Sphinx's body from the stone created a vast, open-pit quarry. The millions of cubic feet of limestone blocks removed from around the emerging lion's form were not waste. They became the primary building material for the Sphinx Temple and the Valley Temple of Khafre, which sit directly in front of the statue. This represents a breathtaking efficiency. In one continuous operation, the ancient engineers created a monumental sculpture, excavated a deep ceremonial enclosure, and produced the exact construction material needed for two massive adjacent temples, all without moving a single block more than a few hundred yards. The Sphinx complex was therefore a self-contained industrial loop, a closed system of material flow that epitomized the plateau's overarching philosophy of maximum resource utilization. Yet this loop was not isolated. It was deeply integrated into the plateau's larger logistical network. The labor force carving the Sphinx was drawn from the same rotating pool of corvée workers. Their tools, the copper chisels and dolerite pounders, came from the same workshops supplying the pyramid masons. The water and food that sustained them flowed along the same supply lines from the Nile harbors. The overseers coordinating the Sphinx's precise sculpting answered to the same central administration that managed the pyramid angles. This means the plateau's master planners were not just overseeing one megaproject, but a synchronized portfolio of them. They had to allocate manpower and materials between the additive construction of the pyramids and the subtractive excavation of the Sphinx enclosure, ensuring neither operation starved the other of critical resources. The timing was likely staggered and strategic. The initial rough quarrying of the Sphinx core may have occurred early, providing stone for Khafre's valley complex just as his pyramid's construction was accelerating. The finer sculpting of the details, the paws, the face, and the ceremonial beard could have continued for years as a specialized task running alongside the final casing work on the pyramids. This reveals an operational sophistication that rivals any modern project management. The Giza Plateau was a multi-threaded processor, executing several colossal tasks in parallel, each feeding into the other, all orchestrated by a bureaucracy that could think in 4 dimensions, managing space, material, labor, and time as a single, fluid equation. The silent Sphinx, therefore, is more than a guardian. It is permanent proof of that synchronized industrial mind, a monument carved not just from stone, but from the very efficiency of the system that built the world around it. These stone-paved highways were the sacred arteries of the entire Giza complex. Stretching for hundreds of yards, each massive causeway formed a direct, enclosed corridor connecting a pyramid's valley temple by the water to its mortuary temple at the base of the monument. In the official ritual, these were processional roads for the king's final journey, a symbolic ascent from the world of the living to the realm of the eternal. But to see them only as ceremonial pathways is to miss half of their genius. During the decades of construction, these causeways would have served a vital, practical purpose as the primary protected supply lines for the entire operation. Their design reveals a dual function, blending profound spiritual meaning with cold, hard logistical necessity. Imagine the Valley Temple not as a quiet chapel, but as a bustling riverfront dock. Barges laden with grain from the royal estates, with copper ingots from Sinai, with fine Tura limestone, would arrive at its quays. From that point, the supplies had to travel up the steep incline of the plateau to the workers' city and the growing pyramid. The causeway provided the perfect solution. Its solid, paved floor, often made of massive limestone blocks, created a stable, all-weather road. Unlike the temporary hauling tracks on the open desert, this surface would not turn to mud during a rare rain or become rutted and treacherous. Its enclosed walls, which in some sections were roofed over, shielded the movement of materials and personnel from the relentless desert sun and wind-blown sand. This was a controlled environment, a dedicated conduit for the lifeblood of the project. The types of supplies moving along these stone arteries would have varied. While the multi-ton core blocks were likely hauled on more direct ramps from the quarries, the causeway was ideal for a constant flow of lighter, essential goods. Teams of porters could carry baskets of tools from the riverside workshops up to the plateau. Scribes and overseers would use the direct route to move between the administrative hub at the Valley Temple and the worksite. Most importantly, the daily sustenance for the workforce, the bread, beer, and fish, could be transported efficiently. Instead of a chaotic scramble up a sandy slope, food could be moved in an orderly, protected manner, ensuring that the vital calorie pipeline to the workers' city remained unbroken. The causeway turned a difficult, exposed climb into a manageable, routine commute. Building these monumental roadways was a significant logistical undertaking in its own right. Each causeway required precise engineering. Surveyors first had to grade the natural slope, carving out a level foundation or building up embankments to create a gentle, consistent incline from the valley to the plateau. This alone involved moving thousands of tons of earth and rubble. Then came the construction of the roadbed itself, laying down large foundation stones and paving slabs that could withstand constant traffic. The walls, sometimes decorated with intricate reliefs of the king's divine journey, were built from more finely cut stone. The volume of material dedicated to these connecting corridors was immense, representing a major investment of labor and resources. This investment makes perfect sense when you view the causeway not as an afterthought, but as critical infrastructure. It was the permanent, durable link that tied the aquatic supply chain of the Nile directly to the beating heart of the construction site, a fixed piece of the industrial machine designed to last for the duration of the project and beyond into eternity. 500 miles upriver from Giza, the landscape transforms from fertile valley into a world of harsh, sun-baked rock. Here, at Aswan, the Egyptians found the ultimate building material, a stone worthy of a god-king's eternal chamber. The red granite quarries are not merely pits, they are theaters of immense patience where the goal was to wrestle perfection from the heart of the earth. The site itself is a testament to ambition frozen in time. You can still see the trenches cut around abandoned obelisks and the sheer, scarred faces of bedrock where monolithic blocks were pried free. The method here was a brutal symphony of persistence. Using only stone tools harder than the granite itself, workers would pound the rock with dolerite balls. They did not cut, they pulverized, reducing the crystalline stone to dust along a precise line, grain by agonizing grain, until a multi-hundred-ton block was isolated from the living mountain. This process could take months for a single beam intended for a pyramid's burial chamber. Once isolated, the block had to be lifted from its trench. Evidence suggests they used a clever trick with sand, packing the space beneath the stone and then slowly draining it out, lowering the colossal weight gently onto a prepared bed of timber and rubble. But freeing the block was only the first victory. Now it had to begin the most perilous journey of any component in the entire Giza project. The first leg was a short, terrifying slide from quarry to riverbank. Workers would have constructed a heavily reinforced transport road, a track of compacted earth and timber leading down to the Nile's edge. They likely used a system of levers and ropes to inch the block onto a massive wooden sledge. Then, with teams of oxen and hundreds of men hauling on ropes, they would guide the sledge down the slope, a controlled descent where a single snapped rope could mean disaster. The destination was a specially constructed loading dock, a stone jetty extending into the deeper water of the Nile. Waiting here was the only vessel capable of such a cargo, a barge of almost mythical proportions. These were not ordinary reed boats. To carry 50 or more tons of granite, they had to be colossal, seagoing style ships built from timber Egypt did not possess. Primary material was cedar, imported from the distant forests of Lebanon. This wood was strong, resistant to rot, and could be fashioned into hulls over 200 feet long. These ships were essentially floating fortresses of timber, built in shipyards near the quarry, and likely partially dismantled after each delivery to be reused. Loading the granite beam onto this barge was an engineering feat in itself. Researchers think they may have floated the barge next to the jetty at high water, secured it, and then carefully winched the stone block across timbers and onto the deck, perhaps by flooding compartments to lower the hull, positioning the block, and then pumping the water out to rise again, gripping the stone securely. With the granite secure, the voyage began, a 500-mile float downstream. This was not a leisurely cruise. It was a high-stakes logistical operation timed with celestial precision. The only safe window for such a heavy, deep-draft vessel was the annual inundation when the Nile swelled over its banks. The higher water provided a deeper channel, reducing the risk of the barge running aground on a hidden sandbar, a mishap that could sink the entire mission. Even with the flood, the journey was fraught. The barge would be at the mercy of the current and wind. Teams of oarsmen and pilots with long poles would work constantly to keep it in the main channel, avoiding whirlpools and treacherous bends. The voyage could take several weeks, a slow, vigilant procession past the entire length of Egypt. All the while, the precious cargo, representing a year or more of quarrying labor, sat exposed on the deck, a single storm or catastrophic leak away from being lost to the river forever. This chain, from the pounding stones in the Aswan quarry to the barge nudging against the Giza dock, represents a supply line of staggering complexity. It required specialized mining knowledge, advanced shipwright skills, imported materials from another kingdom, and flawless timing with the natural world. All of this effort, this entire parallel industry, was dedicated to delivering a few dozen blocks of specific stone for the most sacred, hidden rooms of the pyramids. It underscores a profound truth about the Giza project. The most difficult materials were reserved for the places meant to last for eternity, and no logistical nightmare was too great to achieve that end. The stone was only half the story. To move those granite monoliths, the Egyptians needed a machine of equal magnitude, a vessel built from a material their own land could not provide. The river barges that carried 50-ton blocks from Aswan were not made of local acacia or sycamore fig. Those trees produced timber suitable for small boats, furniture, or roof beams, but not for the colossal, seagoing hulls required to become a floating foundation for a mountain's heart. For that, Egypt looked north across the Mediterranean to the fabled cedar forests of Lebanon. This tree, the cedar of Lebanon, was the ancient world's supermaterial. It grew straight and tall to immense heights, Its wood was strong yet relatively lightweight, aromatic, and naturally resistant to rot and insects. For shipbuilding on this scale, it was irreplaceable. Securing it meant that the Giza supply chain was not merely national but international, stretching across open water and relying on diplomacy as much as engineering. This created a parallel maritime logistics operation, one that began in the mountainous highlands above the coastal city of Byblos. Egyptian expeditions, likely sponsored directly by the royal court, would sail to this distant port. These were not raids but sophisticated trade missions, a form of early state-sponsored commerce. In exchange for the precious cedar logs, Egypt offered goods it had in abundance: gold from the eastern desert, fine linen, papyrus, and grain. At Byblos, teams of local woodsmen would fell the giant cedars, trimming them into massive logs. These logs then faced a treacherous journey from mountain to sea. They were likely lashed together into rafts or loaded onto Phoenician coastal ships for the short trip to the main port. There, they were transferred to the waiting Egyptian vessels, which had sailed empty from the Nile Delta specifically for this cargo. The return voyage across the Mediterranean was the most dangerous leg. Laden with heavy timber, the ships had to navigate open seas, a task far more perilous than river travel. A storm could scatter a fleet and send a year's worth of timber and the sailors who hauled it to the bottom. Assuming a successful crossing, the fleet entered the Nile Delta. But the journey was far from over. Giza lay hundreds of miles upriver. The cedar logs, each one a valuable asset, now had to be transported against the Nile's current. This was likely achieved through a combination of sailing when the wind was favorable and the brutal, relentless work of towing from the riverbanks. Teams of men on foot pulling on long ropes would have strained against the flow, inching the heavy-laden barges southward in a slow, arduous procession. This upstream haul added weeks or months to the timeline, a constant expenditure of human energy dedicated solely to bringing the means of construction to the plateau. Once finally at Giza, the logs were offloaded at the same harbors that received stone and grain. They entered a specialized industrial zone, the Royal Shipyard and Carpentry Workshop. Here, teams of shipwrights, perhaps with knowledge passed down from Levantine craftsmen, set to work. Using copper saws and adzes, they shaped the cedar trunks into the massive hull planks, keels, and ribs for the granite-carrying barges. The construction of a single such barge was a major project in itself, consuming months of skilled labor and a significant portion of the imported wood. But the cedars used did not end at the waterline. The same strong, long timber was essential on the construction site itself. While sledges for hauling could be made from local wood, the most critical levers, used for pivoting multi-ton blocks into precise position or for the final adjustments high on the pyramid face, required the unyielding strength of cedar. Scaffolding platforms allowing masons to work on the upper courses needed a framework that would not splinter under the weight of men and tools. Even the largest roofing beams for the mortuary temples, spanning wide spaces without support, may have relied on these imported logs. Every aspect of this cedar pipeline reveals the expansive, interconnected nature of the Old Kingdom world. The Giza Plateau was not an isolated building site. It was the terminus of a network that tapped into the resources of an entire region. It required stable diplomatic relations with Byblos, a city whose name would become the Egyptian word for book because papyrus was traded through it, highlighting the deep cultural and economic ties. It demanded a navy capable of blue-water Mediterranean voyages, and it wove together the labor of Lebanese woodsmen, Egyptian sailors, delta tow teams, and Giza shipwrights into a single, purpose-driven chain. The silent cedar logs, therefore, were more than timber. They were the physical strands of diplomacy and trade, without which the mountains of stone would have remained forever grounded. The true measure of a civilization's logistical prowess is not in its grandest monuments, but in how it handles its most mundane problems. While the pyramids rose skyward, a city of 20,000 generated a less celebrated but equally monumental output, a constant growing tide of waste. Every day, the settlement produced thousands of pounds of human waste, food scraps, ash from countless fires, worn-out tools, and a blizzard of stone chips from the masons' yards. Left unmanaged, this refuse would have swiftly transformed the plateau into a festering, disease-ridden wasteland, crippling the workforce and halting construction. The silent, unsung triumph of Giza's engineers was creating an invisible sanitation system that kept the machine of creation clean. Consider the sheer volume. A single person produces on average about 1 pound of solid waste per day. For a population of 20,000, that is 10 tons of human waste alone, every single day, year after year. Add to that the bones and scraps from butchering cattle and fish, the chaff from grain processing, the ashes from bakeries, kilns, and domestic fires, and the mountains of limestone dust and fragments from the quarries and workshops. The plateau would have needed to process hundreds of tons of material weekly just to stay ahead of the accumulation. The first line of defense was organized collection. The workers' city likely had designated latrine areas, simple pits or trenches that could be filled and covered over systematically. Waste collection crews, a thankless but vital assignment, would have been responsible for managing these sites, using ash or sand to control odor and pests before transporting the material to designated disposal zones. This was not a task left to chance. It was a scheduled, supervised operation as crucial as delivering stone. Industrial waste required its own solutions. The endless rain of stone chips and powder from the masons' yards was not merely swept aside. This debris had immense practical value. Crushed limestone was a primary component in the gypsum mortar used between the pyramid's blocks. It was also used as a stabilizing aggregate in the mud bricks for ramps and buildings, and as a surfacing material for hauling roads. In a brilliant closed-loop system, the waste from shaping the monument became part of the glue and infrastructure that held the project together. Even worn-out copper tools, once resharpened beyond use, were not thrown away. The metal was far too valuable. These stubs were collected, sent back to the on-site workshops, and melted down in clay crucibles to be recast into new chisels and saws. This recycling ethic conserved precious resources that had traveled hundreds of miles, ensuring nothing was truly wasted. The most critical driver of this hygiene system was not convenience but survival. In a dense, pre-modern settlement, contaminated water and food are a fast track to disaster. An outbreak of dysentery, cholera, or typhoid could decimate the workforce in a matter of weeks, bringing the entire decades-long project to a catastrophic halt. The planners understood this intimately. By rigorously managing waste, they protected the settlement's water supply, likely drawn from wells or transported in jars from the Nile. They controlled vermin and insect populations that could spread illness. The systematic removal of food waste and the use of ash for covering latrines helped prevent the spread of pathogens. This was preventative medicine on a colossal scale, a non-negotiable investment in the health of the human engine. The clean, orderly site we envision was not an aesthetic choice, it was a functional imperative. A cluttered, filthy worksite is a dangerous one where trips, falls, and infections multiply. By maintaining clear pathways, designated disposal areas, and clean living quarters, the overseers minimized accidents and maintained the steady, reliable pace of work that the project demanded. The invisible work of the sanitation crews, therefore, was as foundational to the pyramid's rise as the quarrymen or the masons. It was the daily, unglamorous battle against entropy itself, ensuring that the city of builders could thrive in the shadow of the stone mountain they were creating. Silence was a luxury the plateau could not afford. Amidst the roar of quarrying, the rhythmic pounding of chisels, and the constant shuffle of thousands of feet, a different kind of sound held everything together, the language of coordination. With no radios or telephones, site managers orchestrated this industrial ballet using a symphony of simple, brilliant signals. Visual and auditory codes became the nervous system of the operation. On a clear day, a system of colored flags or banners, raised on tall poles at key vantage points, could relay basic commands across the sprawling site. A green flag signaling a clear ramp, a red one halting traffic after an incident. For synchronizing the most physically demanding tasks, sound was king. The deep, resonant beat of a large drum or the blast of a horn could cut through the ambient noise. Imagine the moment a 50-ton granite block needed to be inched forward on its sledge. A foreman, perched atop the stone, would not shout, his voice lost in the wind. Instead, he might raise a hand. A drummer, watching intently, would strike a single, booming note. On that beat, 200 haulers leaned into their ropes as one, their combined muscle translating sound into motion. A different drum pattern might signal a shift change, calling a fresh crew from the barracks while the previous team moved to the bakeries. This real-time coordination handled the immediate rhythm, but the complex plans themselves traveled in the hands of runners. Young, agile messengers, knowing every pathway and ramp, would sprint between the central administration, the quarries, and the rising pyramid faces. They carried the day's critical data, a limestone flake called an ostracan, with a scribbled note from an architect to a foreman. The message might specify the exact dimensions for the next batch of casing stones from the Tura quarry, or alter the hauling route because a ramp section was under repair. This constant flow of hard information prevented the chaos of 20,000 people working from memory or guesswork. The foundation of all these instructions was a universal language of precision, the royal cubit. This was not a vague approximation. It was a standardized measurement rod, roughly 20.6 inches long, reproduced in wood and stone and distributed to every foreman and mason on the plateau. When an architect's schematic called for a block to be cut to 10 cubits long, every workshop understood exactly what that meant. This eliminated costly errors and ensured that a block shaped in a quarry miles away would fit perfectly into a waiting space on the pyramid's north face. Written orders on papyrus scrolls, though fragile and mostly lost to time, would have contained the higher-level plans, the monthly material quotas, and the labor allocations for different zones. This layered system, from the instant drumbeat to the carefully preserved scroll, created a seamless flow of intention. It turned the shouted chaos of a massive worksite into a coherent conversation, where a single idea from a planner in a shaded office could become, within hours, the precise action of a team high on a sun-baked ledge, all connected by a web of signals, runners, and shared measurement. The final, most profound coordination was not between men and stone, but between the entire plateau and the cosmos itself. Aligning a 480-foot-tall pyramid to the four cardinal directions with an error of less than a fraction of a degree is not a feat of strength. It is a triumph of knowledge systematically applied at a staggering scale. This precision required its own flawless logistics, a supply chain not of materials but of celestial data and geometric truth, distributed perfectly across a miles-wide work site. Before the first foundation trench was dug, teams of astronomer priests performed the critical, invisible work. To find true north, they likely used the circumpolar stars, those that never set. By observing the rotation of the heavens around a fixed point, they could identify the celestial pole. A simple but brilliant tool called a merkit, a notched palm rib with a plumb line, allowed them to sight on a specific star at its eastern and western culminations, bisecting the angle to pinpoint north. This astronomical data was the project's first blueprint, more vital than any quarry plan. Transferring that single point of celestial alignment to the chaotic, rocky ground was the next monumental task. Surveyors would have driven a central stake marking the determined north. From this sacred datum, they used knotted measuring cords, stretched taut and checked against the royal cubit standard, to mark out the perfect square base, each side over 750 feet long. Ensuring this gigantic square was not just aligned but perfectly level presented another Herculean problem. The Giza Plateau is not flat, it slopes noticeably. To create a level foundation for millions of tons of stone, the builders engineered one of history's first and largest surveying networks. They likely cut a grid of shallow trenches across the entire foundation area and filled them with water. Water, they knew, always finds its own level. By marking a consistent water line on the trench walls, they could establish a level benchmark at every point across the vast site. Teams of laborers then cut down to this benchmark, removing bedrock in some areas and building up in others, until the entire footprint was a flawless, horizontal plane ready to receive the first course of stones. This was quality control on a geographic scale. The true logistical marvel was ensuring that this initial, perfect alignment was maintained for decades as the structure rose into the sky. The architects could not afford a cumulative error. Every single block placed by thousands of different hands over 80 years had to contribute to the perfect geometry. The solution was constant verification. As each new course was laid, surveyors would check the alignment from the corners inward, using the same stellar observations to ensure the growing edges remained true. They employed simple but effective tools like the A-frame level, a wooden device with a plumb line, to check that each layer was perfectly horizontal before the next began. This meant the flow of information was as critical as the flow of limestone. The astronomical north, determined at the project's dawn, had to be communicated and re-verified for every foreman and mason, season after season. It was a logistical challenge of memory and discipline, ensuring that the original intention set by the stars was never lost in the dust and noise of daily labor. The pyramids, therefore, are not just piles of rock. They are crystallized equations, permanent proof that this civilization had mastered the logistics of thought itself, scaling a single, perfect idea into a mountain. The mountain had reached its full height, a colossal stepped core of rough limestone waiting for its final skin. This was the project's last great logistical sprint, the application of the brilliant white Tura limestone casing. Tens of thousands of these premium blocks, each one a masterpiece of precision, now had to be delivered, shaped, and locked onto the sloping faces to transform a jagged stairway to heaven into a perfect geometric light. The challenge was one of ultimate finish work on a literally monumental scale. Each casing block was not a simple rectangle, it was a complex trapezoid. Its back face had to fit snugly against the uneven core masonry, while its outer face had to be cut at the exact angle of the pyramid's slope, 52 degrees, and its top and bottom surfaces had to be perfectly parallel to the pyramid's base, not to the horizon. A single block misplaced by a fraction of an inch would throw off the entire run of stones above and below it, creating a visible ripple in the smooth plane. The masons responsible for this final act were the elite of their craft. Working at staging areas near the pyramid's base, they used copper saws and abrasives to achieve a finish so smooth that the joints between blocks were often invisible, reportedly less than a 50th of an inch wide. This was not construction, it was jewelry making performed on stones weighing several tons each. The delivery of these finished stones became its own precise ballet. They could not arrive too early, as storing them on the crowded plateau risked chipping and damage. They had to flow in a continuous stream from the Tura quarries, 8 miles downriver, timed perfectly with the progress of the casing teams. Each barge load represented a week's output from a distant quarry, and its contents had to be catalogued by scribes the moment it docked, matched to a specific waiting space on the pyramid's face. This created a just-in-time delivery system of breathtaking ambition, where a delay in the limestone supply would leave hundreds of the most skilled masons idle, a costly waste of expertise. The most intriguing puzzle is how they physically placed these stones on the upper reaches of the pyramid. A prevailing theory suggests the builders worked from the top down. Imagine the final construction ramp, whether straight or spiral, still clinging to the pyramid's side, reaching all the way to the summit. Workers used that ramp to bring the final capstone, the pyramidion, to the top and set it in place. Then, as they dismantled the ramp layer by layer, they worked backward down the pyramid. Starting at the top, they would case a section of the exposed core, creating a smooth, finished apex. Then they would remove a section of the ramp below it, revealing more rough core, and case that new section. This method solved multiple problems at once. It used the ramp's own material, the millions of tons of mud brick and rubble, as a working platform for the final phase. Dismantling the ramp provided a steady flow of material that could be repurposed for other projects or simply discarded, clearing the plateau. Most importantly, it allowed the casing crews to always work on a level surface, the remaining ramp, right in front of the face they were covering. They could slide each heavy, finished block directly from the ramp onto its prepared bed of mortar, making the delicate final adjustments without dangling from ropes hundreds of feet in the air. This reverse logistics operation, building downward while dismantling the very structure that enabled the ascent, is a signature of the Giza mind, a system where every action served multiple purposes. The final act was a polishing that turned the plateau into a mirror. Teams with abrasives would have smoothed the white limestone faces under the sun, creating a surface so reflective that the pyramids would have gleamed like beacons across the Nile Valley, a fitting culmination to an 80-year project that mastered not just stone but light itself. The gleaming white pyramid now stood alone against the sky, a silent monument to perfection, but the plateau surrounding it told a different story, a landscape of utter chaos. The final and perhaps most overlooked logistical phase was not about building up but about tearing down. For years, the Giza Plateau had been a sprawling industrial city, a tangled web of ramps, roads, workshops, and barracks. Now, with the last casing stone polished, the entire machine had to be carefully dismantled and erased. This was not a haphazard abandonment. It was a deliberate, planned deconstruction, the final act of the grand design. The goal was absolute, to leave only the pristine, eternal monuments, as if they had risen from the desert by divine will alone, with all evidence of the human effort that created them swept cleanly away. Imagine the scale of this clean-up operation. Millions of tons of mud brick and rubble from the massive construction ramps had to be removed. The miles of prepared transport roads, worn deep by countless sledges, needed to be broken up and leveled. The entire workers' city, Heit el-Ghurab, with its barracks, bakeries, and administrative buildings, had to be systematically taken apart. Even the harbors and canals at the base of the plateau likely required infilling or redirection to restore a more natural landscape. This was a project rivaling the initial site preparation in its sheer volume of moved material. Yet, for the ancient Egyptians, this was not waste disposal. It was resource recovery on a colossal scale. Every piece of the temporary city held potential value for the next royal project. The most precious material was timber, especially the imported cedar used for levers, scaffolding, and barge construction. This wood was far too valuable to burn or abandon. Teams would have carefully disassembled the heavy lifting gear and the frames of the workshops, sorting the long cedar beams for transport. These would be shipped down the Nile to be reused in temples, palaces, or the next pyramid project, perhaps at Abu Sur or Saqqara. The mud bricks from the ramps and barracks, made from Nile clay and straw, were a reusable commodity as well. While not as durable as stone, sun-dried bricks could be crushed and remixed with fresh straw and water to form new bricks for other state buildings or enclosure walls. Even the rubble, the limestone chips and desert clay, could be repurposed as fill for foundations or roadbeds elsewhere. This systematic recycling reveals the economical, long-term thinking of the state. Nothing was truly single-use. The life cycle of every material was considered from quarry to final decommissioning. The process of dismantling had to be as organized as the construction itself. They could not simply knock down the ramps, as an uncontrolled collapse might damage the newly finished pyramid faces or the surrounding temples. It likely proceeded in reverse order, a mirror image of the build. Workers would have started at the top of the ramps, carefully disassembling the upper sections and lowering the material down in controlled loads, using the same rope and lever techniques that built the mountain. The workers' city was not violently razed but methodically taken apart, room by room. Roof beams were salvaged, usable mud bricks were stacked for transport, and only the poorest materials were left to be scattered by the wind. This erasure was so thorough that for millennia, the world saw only the result, the solitary pyramids, and not the frantic, ingenious human world that created them. The empty desert we see today is not the natural state of the Giza Plateau during its age of creation. It is the curated final exhibit, a stage cleared of all the scaffolding, machinery, and sweat, leaving only the perfect, silent performers to take their eternal bow. The true scale of the Giza project is measured not just in stone, but in what was consumed. To power this 80-year endeavor, the civilization effectively redirected the entire ecological output of its kingdom, creating an ancient carbon footprint of breathtaking proportions. This was not an incidental side effect, but a calculated expenditure, a testament to how completely the state could harness the living world to serve its vision. We can begin with fire, the essential force behind the metal that shaped the stone. Smelting the millions of copper tools required an endless supply of charcoal. This charcoal came from trees, primarily the acacia and sycamore fig that grew along the Nile. To produce enough charcoal for the constant cycle of tool making and repair, vast stands of timber would have been systematically harvested. Teams of woodcutters would have operated like a permanent expedition, moving along the river to fell trees, cut them into manageable pieces, and then slowly burn them in covered pits to create the pure carbon fuel needed for the furnaces. The scale of this demand was likely staggering, representing the gradual clearing of entire stretches of riverside forest, an ecological transformation driven by the insatiable appetite of the workshops on the plateau. Beyond fuel, timber was a structural necessity. While the great cedar logs for ships and levers were imported, the millions of sledges, the scaffolding, the tool handles, and the roofing for barracks all came from local woodlands. The construction ramps, built from millions of mud bricks, still required wooden formwork and reinforcement. Each sledge, hauling stones for years, would splinter and wear out, needing replacement. This constant drain on wood resources would have visibly altered the landscape around the capital region, turning wooded areas into managed plots and then into barren ground. The quarrying operations, while sourcing stone, also represented a permanent alteration of the earth. The great pits at Giza and Tura are not just holes, they are the removal of entire geological formations. The dust from this constant cutting and pounding would have settled over the surrounding desert and the workers' settlement, a permanent haze in the air breathed by every laborer, a tangible reminder of the mountain being unmade to build another. Perhaps the most profound diversion was not of stone or wood, but of life itself. The agricultural surplus that fed the workforce represented the redirected labor of the sun. The grain consumed by 20,000 people each day was energy captured from the Egyptian sky by countless farmers, energy that was then funneled through the state's logistics into the muscles of the builders. This was the kingdom's photosynthetic output being converted into architectural ambition. The cattle herds that provided occasional meat were resources that could have been used elsewhere. Their very existence managed to punctuate the workers' calendar with festivals of shared consumption. This mobilization of biological resources, the forests for fuel, the fields for food, the river for transport, shows the project as a total ecological event. The pyramids, therefore, stand as monuments to a civilization's ability to temporarily reorganize its entire relationship with its environment, concentrating decades of natural growth and seasonal cycles into a single, immutable point on the horizon. The ultimate cost of this logistical triumph was paid in the quiet, steady transformation of the land itself, a price rendered invisible by time but written clearly in the scale of the achievement. The silent, empty plateau is the final testament to a system that had perfected its own disappearance. Yet the true legacy of Giza was not left in the sand, but embedded deep within the machinery of the state itself. The logistical frameworks forged in the heat of that 80-year project did not vanish with the ramps. They became the permanent operating system for one of history's most enduring civilizations. The administrative bureaucracy, born from the need to track millions of stones, evolved into the spine of Egyptian governance for the next 2,000 years. The network of scribes, overseers, and regional governors first proven on the construction site became the template for managing the entire Nile Valley, from tax collection and grain storage to law and foreign trade. The pyramid project was the ultimate stress test, and the systems that passed it became the default settings for empire. That revolutionary labor model, the seasonal corvée system, was refined at Giza into a sustainable national engine. It demonstrated that a pharaoh could mobilize a vast percentage of his population for grand projects without triggering collapse, so long as it was synchronized with the river's flood and supported by a reliable food supply. This understanding became a fundamental tool of royal power. Every major pharaoh who followed, from the builders of the later pyramids at Abusia and Saqqara to the creators of the monumental temples at Karnak and Luxor, drew upon this same playbook. They called upon the farmers during the inundation, housed and fed them from central stores, and organized them into specialized gangs under familiar hierarchies. Giza proved the model worked on a colossal scale, and so it was repeated again and again, becoming a cultural rhythm as predictable as the Nile itself. Perhaps the most far-reaching innovation was the mastery of long-distance supply chains. Before Giza, moving 50-ton stones 500 miles was an unimaginable feat. After Giza, it was a solved problem. The knowledge of how to quarry at Aswan, build cedar barges, and navigate the flood current became institutional memory, held by the state's expedition leaders and shipwrights. This logistical confidence allowed later pharaohs to dream bigger and source more diversely. Obelisks of solid granite could be commissioned with the certainty they would arrive. Exotic woods, precious metals, and rare stones from Nubia, the Sinai, and beyond could be integrated into building plans because the transportation network, first pioneered for pyramid cores, was now a permanent royal asset. The state now had the reach to turn the entire region's resources into expressions of its own power. In this light, every subsequent monumental project in Egyptian history is a direct descendant of the Giza operation. The Valley of the Kings, with its hidden tombs carved deep into desert cliffs, required the same precise management of a remote, rotating workforce and the same clandestine supply lines. The sprawling temple complexes of the New Kingdom, built over centuries by successive rulers, relied on the same enduring bureaucratic structures to manage decades-long construction timelines and the dedicated estates that funded them. The organizational chart had been written on the Giza Plateau, and every generation of architects and viziers simply copied it for their own chapter. Therefore, the most profound invention at Giza was not the geometric form of the pyramid, impressive as it was. the lasting breakthrough was the logistics of mega construction itself. The ancient Egyptians discovered how to convert political will and economic surplus into permanent, awe-inspiring reality. They crafted a repeatable process for turning the collective effort of a civilization into a single point of focus, a mountain of meaning. This operational blueprint for planning, for supply, for human management became the hidden foundation of pharaonic authority. It allowed the idea of kingship to build itself in stone, generation after generation, long after the last worker left the Giza Plateau and the desert winds began to erase all traces of the machine that had once hummed there. The pyramids were the spectacular, final product, but the true wonder was the factory that built them, a factory whose blueprints would run an empire for millennia. The silent pyramids are the final, frozen frame of a motion picture that lasted 80 years. We have spent our time not admiring the static peak, but reconstructing the roaring, living machine that built it. The true wonder is not in the stone that remains, but in the invisible system that vanished, a system of synchronized movement on a scale the world would not see again for thousands of years. This was not magic, it was management. It was not mystical, it was logistical. The real monument at Giza is the process itself, the first great industrial complex where the entire output of a civilization was channeled into a single, breathtaking point of focus. This understanding fundamentally changes our view of ancient Egypt. They were not merely a society of priests and pharaohs obsessed with the afterlife. They were one of history's first and most brilliantly capable project-based civilizations. They were master architects of time, labor, and supply chains long before those terms even existed. They solved problems of resource allocation, quality control, and long-term planning with a sophistication that feels startlingly modern. When you look at the Great Pyramid now, try to see past the geometry. See the bakeries producing thousands of loaves, the scribes tracking shipments of cedar, the drumbeats coordinating 200 haulers on a single rope, and the astronomers transferring a star's position onto a desert floor. See the dynamic, humming world that made the static wonder possible. This perspective invites us to look differently at all the ancient marvels that dot our planet. The stone circles, the lost cities, the colossal statues, each one is not just an object, but the endpoint of a vast and vanished human enterprise. What other invisible systems, what other forgotten logistics, lie buried in the stories we think we know? If you enjoyed this deep dive into the hidden engine of history, be sure to subscribe. We are just getting started uncovering the intricate human realities behind the world's greatest mysteries.